Welcome to Data Science with EJD. In this video, we are still on with unsupervised learning, which is under machine learning. I've been talking about the broad field of data science in general. Okay, since we started unsupervised learning, we've seen some groups of algorithms. The first set were the clustering algorithms. Then later we saw the dimensionality reduction algorithms. And from this video onwards, I think from this video till the next three videos or so, we'll be talking about another group of algorithms under unsupervised learning referred to as association rule learning algorithms, association rule learning. Of course, as the name, as you can see already, it's about the rule for associating things together. That's basically what this is about. So in general, we have machine learning, which makes machines, computers, devices learn from data, and that is then divided into supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is with labeled data, unsupervised learning is with unlabeled data, while reinforcement learning is that situation where, you know, machine learns from data in such that it gets there's a reward for good performance and there's a kind of penalty for bad performance, just like in a game situation like that. So, and we went ahead to see supervised learning where we saw algorithms like classification algorithms and regression algorithms. Then we moved on to supervised learning. And just like I said, we've done things about clustering algorithms and, of course, dimensionality reduction algorithms. So here we are talking about association rule learning. And the first algorithm we are looking at is the a priori algorithm under association rule learning under machine learning. Okay. So the question is, what is a priori algorithm? But first of all, right, since we're talking about association rule, can we just have a kind of insight into that? Association rule learning is a data mining technique that identifies interesting relationships and patterns between variables in large transactional data sets. So you have data sets where there are transactions going on, like in a business setting or whatever, you know. So the a priori algorithm is a classic method for frequent item set mining. So you see the idea of item set. So items that go together, basically, that's what we are talking about. So frequent item sets. So items that are usually purchased together or something like that. So the a priori algorithm is a classic method for frequent item set mining and association rule learning in transactional databases. It is foundational in data mining, especially for market basket analysis. In the next video, we'll be looking deeply into the market basket analysis. So, and that's about discovering which items are commonly purchased together. So, a priori algorithm was proposed by Agrawal and Srikant in their paper in 1994. So, the example of what happens in an a priori algorithm is if customers buy bread and butter, they often buy jam too, right? So, this kind of thing has shown us that bread, butter, and jam have been associated together. So there are applications of a priori algorithm in retail sales analysis, cross-selling recommendations. Somebody comes to buy from you, and then I mean, very good marketers know how to do this. You went to buy a car, and then you bought maybe you bought a jump starter, and then they tell you something like, "Oh, are you sure you don't need a car freshener and things like that?" So that's them cross-selling you right there. Okay. So a priori algorithm is also good for inventory management, for bioinformatics, for finding co-occurring genes, and for web usage mining. So the key word here is co-occurring, like things that go together, things that happen together. So let's look at some key concepts and terminology of a priori algorithm. So first thing, we have what is called an item. An item is simply a single object in a transaction, e.g. milk. Then we have an item set, which is a group of one or more items. That's more like a set, e.g. milk and bread. Then you have a transaction, which is a collection of items bought together. You have a support, which is fraction of transactions containing an item set. That is what we call support. And then there's confidence. That's the likelihood that if a transaction has A, it also has B. Then you have lift. Lift is how much more likely A and B occur together than if independent, right? So what is the chance that A and B occur together than being separate. Okay. So how a priori works, we look at this step by step. So the idea is this uses the a priori property, and the a priori property is basically that all subsets of a frequent item set must also be frequent. So if there's a frequent item set, all their subsets must also be frequent, and that's the idea. That's the a priori property. So if the set is frequent, then the element of the set is also frequent. The elements of the set are also frequent. This enables efficient pruning of infrequent candidates. So let's look at algorithm steps for the a priori algorithm steps. First of all, we have the generate one item set. That's one item. To count each single item support, keep those meeting minimum support, right? So maybe you have a minimum support, right? We already know what support is about from up there. We said support is fraction of transactions containing an item set. So anyone meaning that requirement for minimum support, you keep that, and the next thing you generate candidate k item set, that is k greater than or equal to 2. So one item set, then make it 2. So here you join frequent k minus 1 item set to get new k item sets. Then the next thing is you prune, remove candidates that have infrequent subsets. Then 4, count support, scan database to compute support of candidates. Then 5, keep frequent item sets, retain only candidates meeting minimum support requirements. Then repeat, continue until no more item sets can be generated. So that's the algorithm, the a priori algorithm right there. Now let's look at, you see there's a maths behind everything we've been doing in machine learning. Everything has a maths background to it. So, I mean, the math here, we've seen things like set theory come into play in what we've been talking about so far. And now we are going to an arena where we see something like probability coming into it. And if you need to know more about this set theory, probability and all that, you may want to check my playlists. You have all these videos available in my playlist, or you can also check some of the links to some of these videos are available in the description. So you want to check below. And if you have not subscribed to the channel, this may be a nice place to stop and subscribe to the channel and hit the notification bell so you can always get alerted each time a new video is released. And also, my data code sheets and data sets are available. You'll find a link also to a Google Drive, with between many hash lines, tags like that. So it will lead you to where you find all the documents, all the code sheets, and even slides and all that I use for these classes. So you can download and follow along step by step. Now back to the business. Mathematical foundation of a priori algorithm. So we have the definitions for support. The support A is such that number of transactions containing it. You count all the possible transactions containing it all over total transactions. That's how you get the support. Then you have confidence A to B. So confidence A to B means support A union B all over support A. That's how you get the confidence. Then lift A to B. Lift A to B means confidence A to B. This confidence you've got here all over the support here. So you can see confidence depends on support and lift depends on confidence and support. That's how that goes. So the goal is you want to find all item sets with support greater than or equal to the minimum support. And then you want to generate rules with confidence and lift greater than thresholds, right? So the question is how to use a priori with Mlxtend. Mlxtend, that's machine learning extensions, is a Python library that makes a priori practical. So Mlxtend is a Python library that makes a priori practical. So we have key functions, transaction encoder. So convert transactions to one hot encoded data frame. Then we have a priori, which mine frequent item sets, and you have association rules, which generate rules with metrics like support, confidence, and lift. So let's look at a full Python implementation of a priori algorithm. Let's show the line numbers. Okay, so of course here now we need to we need to install the Mlxtend library. So full Python implementation, step 1, install and import. So we're installing the Mlxtend, which is the new library we're using it. I've done it before. I'm just doing it again. That's why it's saying requirement already satisfied. In your case, you may just have to do it fresh if it is the first time. Then from here now, so do pandas. Now Mlxtend in preprocessing, we need to do transaction encoder, Mlxtend frequent patterns. We get the a priori and association rules from that. Then the next thing is we go for the example data set. So here we are doing a data set, a uh, a self-generated data set, so to speak. So imagine we have the data set milk bread. So this is one transaction: milk bread butter. Second transaction: bread diaper beer eggs, milk bread diaper beer, bread milk diaper beer, bread milk diaper coke. So that's our data set. So we have that. So that's a list of lists. We are making that into a data set here. Then we have the one hot encode. So we have transaction encoder in line one. TE is transaction encoder. So we have T underscore array. That's T dot fit the data set. That data set we have up there. Dot transform the data set. Then we have the data frame. So we are converting that into a data frame. You have PD dot data frame T array column set TE columns. So here we see one hot encoded transactions. So what this means is that in the first transaction, counting is in Python start from 0. So in the first transaction, there was no beer, there was bread. Okay, there were only bread, butter, and milk, right? Bread, milk, bread, and butter. Yeah. So anything that is present in this transaction will be shown as true. Anything that is not present will be false. In the last transaction, we have bread, Coke, diaper, and milk. Bread, Coke, diaper, and milk. Bread, Coke, diaper, milk. So we have all that. So that gives us this. So then the fourth step is to find frequent item sets. So to find frequent item sets now, we have frequent item sets equals a priori, the data frame we have up there. The minimum support is 0.6. So we can change the zero. So this is the minimum support now. So this is the threshold for what we want. Then use column names true. Then so this gives us frequent item sets. So any frequent item set with support that is 0.6 upwards will be shown here. All right. So here now we say having beer alone, that's 0.6. Bread alone is 1.0. So it is sure there will always be bread. Diaper, you have 0.8. Milk, 0.8. Beer and bread together, 0.6. Diaper and beer, you have them like that. So all that. So if we reduce this now to say 0.4, we are going to have now we have 11 items. So if you reduce it, we have more items. We have 15 items. So you want to set your minimum support to based on whatever your needs might be, right? Or if you increase it to say 0.8, we have fewer stuff. So that's how that works. So we have this. Then step 5, generate association rules. So we now want to generate association rules. Now this first line is just to import warnings because we want to ignore a warning that might come because we might have division by zero problems like that. So of course, from Mlxtend frequent patterns, we need association rules. So the rules will be association rules, frequent item sets, which we already got, I think, from up here. We got frequent item set from there. Then the metric is confidence and minimum threshold is 0.7. So then the rules now. So you have rules that drop any not available data, confidence lift are the things we need. So print association rules. So we have the antecedent, consequence, support, confidence, and lift. So we have all of this. So the antecedents, we have beer. After beer, we have bread. And the support for that is 0.6. The confidence is 1.0 and the lift is also 1.0. Antecedent, that's the first thing you get to buy. That's diaper. After diaper, the next thing you want to think about is beer, and the support is 0.6, confidence is 0.7, and so on and so forth. All of this go on like this. So these are the association rules. So we have antecedents, consequence, support, confidence, and lift. So these are the metrics. Support, confidence, and lift are the metrics for measuring association rule learning, behavior, right? So the next thing we go to step 6 where we filter the rules now. So example, you only want to show strong rules with high lift. Maybe you want lift greater than 1 that shows strong association. So you can say high lift rules is equal to rules lift greater than 1. So then you now print high lift rules now. So you now have fewer items because you're only looking for lift greater than 1. So these are the strongest of them all. So we are talking about filter rules now. We not only strong rules with high lift. So diaper and beer diaper bread, and then beer bread, and then diaper, beer bread, and all that. So basically, you have diaper, beer, and bread. They're always occurring in all the situations. Then we can have the output interpretation. So you have the metric and what it tells you. Support tells you how common the item set is in all transactions. Confidence tells you how often the rule holds true. And then lift greater than 1 is tells you about positive association. That means items appear together more often than by chance. Lift equals 1 means the items are independent. Lift less than 1 means negative association, right? They don't occur together. So example, You have antecedent, diaper, consequent after diaper is beer, and the confidence is 1.0. So this means that if someone buys diaper, they always buy bread in this data because the confidence is 1.0. Confidence tells us how often this is true all the time. So once somebody buys diaper, they also buy beer. So this can make you understand behavior of people shopping in your mall or whatever outlet you have. So let's look at some pros, cons, and best practices for a priori algorithm. So first of all, it is okay for the pros now. A priori algorithm is simple and intuitive. It generates interpretable rules and it is well supported in libraries. The cons, the disadvantages, it can be computationally expensive for large data sets and generates huge number of candidate sets, and it is not scalable to big data. So if you have extremely big data, this can be a big issue. Then let's talk about best practices. So use higher support to reduce candidate explosion. All right. So you need higher support to be able to trim down possibilities, right? Then filter with lift and confidence to find meaningful rules. Then for large data, use FP growth, which is more efficient. In the next three videos from now, we'll be talking about FP growth. In the next video, I'll be talking about market basket analysis, which is also based on a priori algorithm. And then afterward, we'll go to FP growth. So if you have very large data, you go for FP growth. So the key takeaway here is that the a priori algorithm is a fundamental tool for finding patterns and rules in transactional data. So with Python's Mlxtend, it's easy to use, visualize, and interpret, right? So we see that a priori algorithm is quite interesting indeed. All right. So, and we have the Mlxtend library that makes it pretty useful to handle, easy to handle. So the priori algorithm is fundamental to for finding patterns and rules in transactional data. And with Python's Mlxtend, it's easy to use, visualize, and interpret. So you have some references here: Agrawal R and Secant R 1994 fast algorithm for mining association rules. Then you have the Mlxtend documentation. You want to check that out. You know, talking about the Mlxtend. Welcome to Mlxtend's documentation. I see all these things right here with an example and all these other possibilities, right? So you also have Hanjay, Kamba, and Hanjay, Kamba M, and Page 2011 data mining concepts and techniques. So with this, we come to the end of this video. Very interesting, talking about association rule learning algorithms, right? Let me know how helpful this is for you. And if there's something you'd like me to try out, feel very free to let me know, right? If you have not subscribed already, you know you're missing a lot. So you want to subscribe and hit the notification bell so you can always get alerted each time a new video is released. Okay. On my channel, you can become a member. So just click on join and you see the possible membership levels you can join and the perks attached to them. All right. Till I come your way again, keep doing data right. Bye.